Assalamu alaikum everyone, I am Sara Javed and welcome back to the channel Data Science Explorers and part 2 of our laptop price prediction series. In the last video, we did the curical work of data cleaning and feature engineering. Now we move to the most exciting part, building, training and evaluating of our machine learning models to see which one can most accurately predict laptop prices. Let's get started with the final touches on our dataset, analyzing and cleaning up low correlation features. We begin by checking the correlation of our numerical features with the price. Correlation tell us how strongly each feature is related to the price. As we can see, RAM and SSD have a strong positive correlation, which makes sense. However, notice the hybrid and flash storage column. Their correlation value are very close to zero. This means they have almost no linear relationship with the price in our dataset. Keeping features that don't provide useful information can sometimes add noise and complexity to the model. So for a cleaner, more efficient model, we will drop these two columns. Feature engineering simplifies the GPU column. Next tackles the GPU column. If we look at the value counts, there are 110 different GPU descriptions. This is far too many for a model to handle effectively. The key is not the exact model number, but the brand as that primary drive of performance and price. So we will enjoy a new feature called GPU brand. We use a simple lambda function that splits the string and takes just the first word, which is the brand name. Intel Nvidia AMD. This reduces 110 unique values down to just a few, making it much easier for our model to learn. Cleaning the new GPU brand feature. After creating our new column, we check its value counts. We see hundreds of entries for Intel, Nvidia and AMD, but there is one single entry for a ARM processor. A single data point is not enough for the model to learn from. It's an outlier that can cause issues, so we will remove this one row from our dataset. Now that we have extracted all the useful information into our GPU brand column, we no longer need the original messy GPU column. We will drop it to keep our dataset clean and focused. Feature engineering simplifying the SYS column, like operating system. We apply the same logic to the operating system column. We have different version of Windows and Mac OS plus Linux and other. For a prediction model, the specific version often matter less than the main operating system family. We will write a function called cat_os to group these. All Windows version become Windows, all Mac version became Mac, and everything else is grouped into other no OS Linux. This simplifies the feature while retaining its predictive power. After creating the new OS column, we drop the original OP system column, preparing data for modeling. With our feature finalized, it's time to prepare for modeling. We split our data into two parts, X which contain all our feature column and Y which our target variable what we want to predict. Curical, we are not predicting the price directly, we are predicting the log of the price Y. As you can see from this distribution plot, the long transform price for a much cleaner bell curve. This normalization helps many machine learning algorithms perform better and converge faster. We just need to remember to convert the prediction back to the actual price at the very end. Now splitting data into training and testing sets. This is a fundamental step in a machine learning. We cannot evaluate our model on the same data it was trained on. That would be like giving a student the exam question and answer ahead of time. So we use train test split to divide our data. 85% will be used for training the model. X train, Y train and 50% will be held back as unseen data to test its real world performance. Building the processing and modeling pipeline. This is the core of our modeling workflow. Our data has categorical column like company, type name, CPU, brand, etc. Model need number. The column transfer with one hot encoder automatically convert these text column into numerical format. We then define our model. We will start with a basic linear regression. To streamline everything, we create a pipeline. This bundle the processing and modeling step together. It's incredibly efficient because now we can just fit on the pipeline. And it handles all the steps in the correct order. The R2 score is 0.80, a sold baseline. A good data scientist never settles for the first model. We will now test a variety of algorithms to find the best one. We will use the exact sum pipeline structure, just swapping out the model. Linear regression, this is a variation of linear regression that helps prevent overfitting. It gives us a slightly better RT score of 0.81. So in the decision tree, this model make prediction by learning a set of if then else rules. It gives us a significant boost to 0.84. Random forest, this is an ensemble model, meaning it a collection of many decision tree. It's one of the most powerful and popular models. And look at the R2 score of 0.88. This is our best performer so far. We have service strong model, but if instead of choosing one, we made them collaborate. This is called a voting regression. It take our top model, random forest, gradient boosting, XGBoost, and extra tree, and lets them vote on the final prediction. We can even assign more weight to the model we truth the most like random forest. And the result, an R2 score of 0.89. This is our high score. By combining wisdom of multiple model, we will created a final model that is more accurate and reliable than any single one of its own. This will be our champion model. Exporting the final model for deployment. Our work is done. We have a highly accurate trained model. The final step is to save it so we can use it elsewhere, like in our web application. We use Python pickle library to save our entire pipeline object as pip.pkl. The file contain everything, the processing step and the train voting regression. We also save our clean data frame for our reference. Part 1, we clean the data. In part 2, we built an incredible machine learning model. Now we bring that model to life by building a live interactive web application that anyone can use. Let's see how it's done. First, we import the necessary libraries. Now let's build the user interface, setting up the web page title and layout, and then creating input fields for user data, and creating numerical and other input fields, calculating pip and handling screen inputs, creating the final input fields like CPU, GPU, OS, the prediction logic and button. So, and there you have it. In just a few lines of Python code, we will wrap our powerful machine learning model into a fully functional web app. This allows anyone, even those without coding knowledge, to use our model. I hope you enjoy this series. Thanks for watching.